All right, so we have another 2.5 sections or so before we're done with basically all of the Calc 2 material. So here's my best case scenario is that we get done with all of it tonight. And that'll leave tomorrow for basically tomorrow and half of Thursday, or not quite half of Thursday. The final exam is a little longer than the first two tests. But my best case goal right now is to have basically all of Wednesday and a big chunk of Thursday for review. So we might leave a little bit for Wednesday, but I'm hoping not. Kind of depends on tonight. So let's go ahead and first thing I want to do is talk about some of the things I saw on the most recent test, which hopefully by now you've looked at your grade, looked at the feedback I gave you, and looked at the solution. If not, I would definitely go consult those things on Canvas. I mean, this test is behind us, but this stuff is going to be on the final again very shortly. So true or false section, some of these went really well. For example, B, I mean, I think most of you know how to apply the divergence theorem. C, most of you applied the root test properly there to show that diverges. D, I think, and this was not totally unintentional, but D was kind of meant to see how well you understood the rationale behind the alternating series test, not just kind of the way it's written. So really, if you have a sequence that decreases to 0, so let's just stick with that sequence for starters. If you have a sequence that decreases to 0, that does not necessarily mean that the series will converge. A good example of that is the series 1 over n. So that sequence decreases to 0, but that series, we've shown over and over again, does not converge. But if you take that sequence that is all positive and decreases to 0, if you take that sequence and alternate it, then that converges. That's basically, D is just a rewording of the alternating series test. So while I'm going through this, I mean, I'm going to run through some of the points I saw overall that I feel are worth discussing. But if you have any specific questions or if you want to clarify something, please let me know. For A, I kind of skipped over A. If you have a sequence that contains no negative terms, then it either diverges or converges absolutely. That's true because, this idea of conditional convergence, that only makes sense for a series that alternates. It's meaningless outside of that context. E was about half and half, true or false for E, but basically, if you have a sequence, so in this case, my larger I am guaranteeing that my smaller sequence A sub n converges. That does not mean anything for my larger sequence B sub n. It could still diverge. So it's all about basically what order you put those sequences in. F is absolutely just a restatement of a theorem we've gone over. G is the converse of it, and we have examples for things that look like G. We have sequences that converge that are not monotone. Short answer, Maclaurin polynomial went well for a lot of you. B was, people did really well on B, which was good. Knowing to compare that with 1 over n cubed. A couple people, even though they gave me the right series, didn't actually test it. What is the root test? Root test and ratio test are things that many of you do very well with, which is really good. E, I don't think I got a correct answer on E, so I'll just go through this a little bit rapidly. But basically, and one thing that you didn't need to do is, I saw a lot of people, not a lot, but more than one person apply the ratio test to this series. to find the radius of convergence, which isn't necessary. I gave that to you for free. So your radius of convergence is 1/3. And I know by the way this term is arranged that 4/3 is the center. So basically I want to subtract 1/3 from that, and I want to add 1/3 to that. That'll give me the full interval. So that comes out to be 1, 5/3. So I saw a lot of answers of -1/3, +1/3, which, yeah, that gives you the right radius, but does not give me the right center. So it's not only about what the radius is, you have to apply that to whatever your center point is. In this case, that center is +4/3. 3, you don't have to answer me if you don't want, but I admit I was curious for 3. Many people for A proved to me, and correctly, that A converges. But very few people did this part right here where I said to give me the value of that sum. So I was curious if that was something you didn't know how to do, or you just maybe blazed through the instructions too fast and missed that was what I asked for. But yeah, if that's something you don't know how to do, definitely look over the solutions. Same with so part A, many people proved to me that converges, and I think C, you can prove to me that converges. Telescope and series are a little more difficult to come up with a sum for, but you can still do it. Again, I'm glossing over these kind of fast, but if you want details, definitely look at the solution online on Canvas. For parts of this, people did pretty well with it. So for A, I saw multiple different approaches for doing A, and I saw success with all of them. For those of you who did it right. So binomial series works, but really so does the derivative of a power series, of a geometric sum. You can do a Taylor series there. Lots of things work. B did not go well at all. I'm not sure I got a correct answer for that one. And then C and D were a little more successful, but I would definitely consult the solution there. Actually, C went fine. It was D that you getting that full interval was. I'm still seeing the issue where, people are finding the radius of convergence and then giving me an interval, but never showing me that they've tested the left and right endpoints. So, yeah, that's definitely part of the job. You gotta test those endpoints as well. And then 5, this went pretty well for a lot of people, which I was happy about because it had been quite a bit since we had done arc length and surface area. But overall, people did pretty well there, especially on part A. Part B, I think, setting these up for a general function, I think that seemed to be the mysterious part for a lot of this, for most of the incorrect responses I got for B. Any questions on the test? I believe I put the solutions in the exam 2 prep area. So definitely go take a look at those sometime before the final if you haven't already. Any more questions about the test? Okay, so a couple things I want to remind you all of, just because I've gotten a few questions about it. So I'm not going to give really specific stats on kind of what the raw averages were on that test, but they weren't great. And a couple things I want to say that. Number one, it wasn't totally unexpected, and that's because I've taught or TA'd for Calc 2 enough to know that the sequences and series stuff is really tricky, and it definitely takes a while to get used to. And Yeah, so on that front, I wasn't really surprised. The other thing that sort of concerns me is from the first test to this one, the homework grades dropped off a lot. The quiz submission rates and grades dropped off quite a bit. So yeah, just one more request to finish strong. There's still the final left, and everything's coming back, including the stuff I have yet to show you. So I'm going to try to make myself as available as I can to all of you this week. So if you need anything, if you want to meet or just get some clarity on something or get some help, please let me know. Send me an email. Yeah, email is probably the best way to get a hold of me. Anything else we need to talk about before we get into where we left off? All right, so last time we got through most of 10.2, which is a thing I'm not sharing with you yet. Hold on. Okay, so section 2 of chapter 10 is all about the calculus of parametric curves. And we left off having done one example with area. So I want to do one more just to kind of get through that. So can anyone remind me how we do this? How do we deal with area in this parametric using these curves that are defined parametrically? And if I can, let's just do a regular Cartesian example. I can kind of motivate it that way to remind you. So if I have, it's going to look really familiar. I've drawn sketches like this a lot. But let's say I have a little dx interval. Really, all I'm doing is splitting up this region into these elementary rectangles, and they're each dx width. And how do I get the heights? That comes from y. And really, I can take that approach and I can apply it to these parametric curves, because really all I'm doing is this. For area, you're so used to seeing integrating over some area, or over some interval, integrating f of x dx. But really what you're doing is that f of x is that's function notation for y, which in this case, we don't have this situation. We might be able to get it, but we don't have y equals f of x. What we have instead is x equals f of t and y equals g of t. So we got these two intermediate functions in terms of t. So what I really want to generalize this as is I'm going to call f of x y instead. So really it's not a different rationale, really. I'm just kind of rewriting it. Still, I'm using an integral to find the area of all these little rectangles. So height of the rectangle is y. Width of each rectangle is elementary dx. And basically now I'm just going to represent this as, in terms of my my parametric function. So y, that's g of t. Dx, that's going to be f prime of t dt. So now I've taken my integral I usually use to find area, and I've got it all translated into t. So really, I could, I already have g of t. I could really easily get f prime of t. The last thing to concern myself with is, how do I find the bounds of this interval? How do I find lowercase a and b? So I want to find the area enclosed by the x-axis and the curve. So Basically, that's what I'm required to do. How would I use that piece of information to find out what my limits of integration are?
Professor, can you repeat the question just one more time?
Yeah, so I know I want the area between the curve and the x-axis. So I'll go ahead and give you just more specifically. I'll say I want the region of this curve that's above the x-axis. So how would I find that interval on the t interval that's going to give me the part of this curve that's above the x-axis?
You just can you solve it like it, in terms of you can convert from the second equation y equals to t minus t squared, and from that you can do something and get t equals in terms of y t equals some y term, and substitute that in this one, and then maybe like that.
So I think that would work. There's probably something a little simpler we could do. So let me repurpose this picture up here. Actually, I'll just draw a new one. So let's say I have a curve that looks like this. Actually, it's the opposite of what I want. And I want to find this region in here. How would I find this point here and this point here? Because basically this is going to be my A. This is going to be my B. How would I find those points where this curve crosses the x-axis?
Would you find where x equals 0?
If I find
y equals 0?
Which one of those? So if I'm crossing the x-axis, what is it that's equal to 0? X or y?
Y.
Y. So that's what I'm going to do. So I'm going to say y equals 0. And that's going to help me find my values of t. Because remember, I want to set this integral up in terms of t. I probably could eliminate the parameter and put these together, but I don't believe that would be any simpler. So I'm going to solve this equation here. Basically, this is just y equals 0. I'm going to find these t values. If I factor out a t, I get t times t minus 2 minus t equals 0. So this gives me my interval of 0, 2, which is kind of the last thing we needed. So from there, I can integrate over this interval 0 to 2. And keep in mind what all these pieces are. Y, I know what y is, but I want to parameterize it. So everything in here needs to be written in terms of t. Then I want dx. What should I use for dx?
The derivative of x.
Yep. So that's going to be 3t squared dt. So I'm going to go ahead and pause here. Are we okay with where this came from? Okay, so before I integrate, I'm going to do some distributing. So 6t to the third minus 3t to the fourth. And from here, just kind of work through it. So 3/2 t to the fourth minus 3/5 t to the fifth. Evaluate it from 2 to 0. 0 to 2. So 3/2 times 16 minus 3/5 times 32, and then the zeros will just all give 0. And does this simplify in any nice way? 24 minus 96 over 5. I believe that comes out to 24 over 5. All right, so that gives me an area of 24/5. More importantly, any questions on that before I move on? Okay. All right, so last thing for this section is arc length. So just to kind of recap of last week, so this curve right here, you know, I think most of you probably still have like this this perception that vertical line test is what determines whether whether you have the graph of a function or not. Which this curve fails. So all that means is that y is not a function of x, but you know, each one of these points along this curve C, each one of these points is a function of a parameter t. So in that regard, it is a function. So because of that, we can use integrals to find arc length for these parametrically defined curves. But first, to kind of build it up, let's think about how we did this for Cartesian curves. So let's just pick one of these lengths right here. So let's go from P0 to P1. Actually, maybe we should choose one that goes to the right just because that's what we're used to. Let's call this point here P3. And if you remember what we did in the past, basically, we split up this curve into these, you know, regularly spaced points. And what I'm getting from these regularly spaced points is I just draw what's called a secant line, a straight line to connect those 2 points. And I'm going to find the length of that. And the way I find the length of that is basically Pythagorean theorem. Dx squared plus dy squared equals ds squared. And we use that to set up an integral. So I have ds squared equals dx squared plus dy squared. And if you recall what we did for Cartesian coordinates, we had the arc length is equal to the integral from a to b of the square root of 1 plus dy dx squared dx. So what we're about to come up with is going to look familiar, but it's going to look a little different in a way that it'll make this more conducive for parametric curves. So I have ds squared. I really want ds, so I'm going to get a square root of dx squared plus dy squared. And then if I integrate both sides, it'll give me s equals the integral of dx squared plus dy squared. So remember, I'm trying to do this for parametric curves. So what does it make sense for the differential term to be in terms of? So basically, I'm filling the blank here. What letter goes after d there? Remember, I'm trying to do this for parametric curves. So remember, this curve here, even though it's not, y is not a function of x.
Would it be t?
Right, so yeah, it'd be t, because each one of these points, x, y, I'll call this one x0, y0, this is going to come from some t value, t0. And these functions right here are, I'll just say f comma g. There's a function that turns t into x and a different function that turns t into y. So yeah, I want to have this integral set up as, you know, this basically the integrand is still Pythagorean theorem. That hasn't changed. And by the way we're partitioning up our curve into these straight lines, hopefully that makes sense why we're doing Pythagorean theorem. Basically, we're just basically manipulating this to look like a bunch of right triangles. But this dx squared and dy squared, Remember, we only have the ability to look at integrals in terms of one variable. So dx and dy, those derivatives really need to be taken in terms of t. So this is dx dt squared plus dy dt squared times dt. So basically this is our kind of our respun definition for an integral to find the arc length for a parametric curve. So hopefully it looks familiar. Hopefully you can see the similarities between the Cartesian one and the parametric variety. Any questions on how that got developed? Okay, so let's do a couple of these. So I want to use an integral to find the arc length along the unit circle. So, and this one is a good one to warm up on because really we should know what the distance, what the length around a unit circle is. But let's do it using the integral we just looked at. So I'll kind of walk you through the first one. I'll let you drive on the next one. But so I'm integrating over some t interval. I'm integrating basically my, the integram, like I said before, is the Pythagorean theorem. As the arc length is just going to give me this pure distance if I make these dx and dy intervals small enough. So what should my limits of integration be for this one?
Would it be -1 and 1? Or 0 and 2 pi?
0 and 2 pi. And I'm going to go ahead and guess that you said -1 and 1 because those are the least and greatest x values.
Yeah.
So I'll just remind you that, if we were writing our integral in terms of x, that would be correct. But we want to have our least and greatest t values. So yeah, 0 to 2 pi. What is dx dt going to be? So a derivative of cosine t will be negative sine t. Derivative of sine t will be cosine t. I got the square root of sine squared t plus cosine squared t dt. All right, do you notice anything yet?
Sine squared plus cosine squared equals 1.
Yep, so this whole integrand, basically you're integrating 1. So from there, I just get t evaluated from 0 to 2 pi. I get 2 pi minus 0 equals 2 pi. And hopefully that was the answer you expected. For basically finding the perimeter of the unit circle. In general, we know this is true. So if the radius is 1, then we should definitely get the length 2 pi. Any questions on this one? All right. Oops, sorry. All right, so I want to find the length of one arch of the cycloid. So we talked about this curve a couple of times on Thursday. But basically what the cycloid is imagine a circle rolling around that has a point drawn at some place on its edge. Then basically as that circle rolls, that point is going to trace out a curve like this. So we want to trace out one arch of the cycloid. So we're integrating from A to B. And I'll kind of put it back on you. So how do I continue?
It would be the square root of dx over dt plus dy over dt squared.
I didn't hear the squared on this first one, but I think you meant it. All right, good. How do I figure out my interval?
Theta equals 0.
What equals 0?
X equals 0, y, that stuff.
So set x equal to 0?
Sorry, y equals 0.
Yeah, so, and why is it y equal to 0? Basically, so I want one arch of this cycloid. So I basically, where does the arch begin and end? It begins where y, so y starts at 0. I'm assuming y starts at 0. I guess I'll find out in a second if that matches this equation. But this right here will give me theta equals A. And this right here will give me theta equals B. So, yeah, let's go ahead and set y equal to 0. And we get r, y, or sorry, 0 equals r times 1 minus cosine theta. I'm going to divide by r. I'm assuming r is a positive constant. Otherwise, this wouldn't make any sense. And I get 0 equals 1 minus cosine theta, or cosine theta equals 1. So when does that happen? What are the first two values of theta where that happens?
0
0 is one of them.
and pi.
And what is
Is it 2
cosine
pi?
pi? 2 pi, right? Yeah, cosine pi is -1. So yeah, we need to go 0 to 2 pi. So let's keep on going with this integral from 0 to 2 pi. What is dx dt?
Would it be 1 minus cosine theta?
Yep. 1 minus cosine theta, all squared. And then dy. It's going to be r sine theta squared. All right. So hopefully some things happen when I try to simplify this. So I get r squared minus 2r cosine theta plus r squared cosine squared theta plus r squared sine squared theta d theta. From there, does anything convenient happen for us? So hopefully you realize that r squared cosine theta plus r squared sine theta, sorry, r squared sine squared theta comes out to be r squared. So then I get 2r squared minus 2r cosine theta d theta.
Why does that equal r squared?
All right, good question. So let's pull it off to the side. R squared sine squared theta plus r squared cosine squared theta equals r squared factored out of sine squared theta plus cosine squared theta, which equals r squared times 1.
Okay, that makes sense.
All right. And I'm looking at my notes. I think this is an integral I decided was not worth the trouble, unless anyone sees a way to handle this, but I don't think there is one. At least not a really quick one. Yeah, so there's a complicated substitution I had to do here. And I think it's more worth our time to move on to surface area. So hopefully you accept that we're going to abbreviate this, but basically that comes up to be 8 times whatever the radius is. And if you want to look more into that, that involves some trig identities, but yeah, I'd rather just move on. All right, any questions on this arc length example? All right, so last thing we're going to look at is going to be surface area. So I'm going to find the surface area of really any sphere. If you don't remember, the surface area of a sphere is 4 pi r squared, and we're going to prove that using all right, so try to make this a circle. Anyway, we're going to take this circle, revolve it around, really by symmetry, I can do either axis. Let's just do the x-axis. Going to revolve that around the y-axis, or around the x-axis. So the first thing I want to do, though, is I'm going to do this in parametric. So I really want to come up with my parametric equations. Or if you'd rather, we can even start with the Cartesian. But basically, I want to try to find the surface area of a sphere. So if I want to deal with a sphere, what type of 2-dimensional graph should I be revolving around the x-axis? I guess what I'm asking is, what is this graph?
A semicircle?
Yeah, we're going to do a semicircle, but I'm actually going to, let's just think of it in terms of a whole circle. Because really, I can just revolve the top half of it by being careful with my parameter. I just didn't draw all of it because I didn't plan for how much room it was going to take up very well. So yeah, the area we're going to deal with, actually I'm not going to shade it in because I need to shade in other stuff. So we're going to take this circle, revolve it around the x-axis, and find that surface area. So actually, let's do this. Let's build up from the Cartesian. Does anyone remember what the Cartesian equation is for a circle? the circle of radius r. We'll say the center is at 0, 0, just for simplicity.
Isn't it y squared plus x squared equals r?
Very close. R squared. Which is really a Pythagorean theorem thing. So horizontal side x, vertical side y. The hypotenuse is essentially r. So basically, this is just another application of Pythagorean theorem. So x squared plus y squared equals r squared. Does anyone remember how we talked about doing this in parametric form? Like what are, if I want to express x and y in terms of some parameter, what have we done in the past? So in general, just remember what cosine and sine mean. Basically, the cosine of an angle basically just gives you the x coordinate of that point on the unit circle. So let me say it in a more elegant way. So let's say my angle is right here. The cosine of that angle is going to be basically whatever this x coordinate is, multiplied by r. The sine is going to be whatever that y coordinate is, multiplied by r. So because of that, you're going to get x equals r cosine theta and y equals r sine theta. So from there, basically we've parameterized this Cartesian equation. So let's recall, how did we find surface area in Cartesian form? So integrated from A to B. Maybe I should draw another picture here to remind you of how this works. So basically, I'm going to take a little rectangle here. I'm going to revolve that around the x-axis. And actually, it's not a rectangle I'm going to draw. It's going to be, basically, I want to mimic a straight line. So I'm doing a wide interval there just to kind of help me. But I'm going to take that and wrap it around the x-axis to make like a little cone-shaped segment, a frustum shaped segment. So because that, basically, I want to get the circumference of a circle. So that's going to be 2 times pi times some radius. In this case, where's the radius going to come from? X or Y?
X
If I'm revolving
or
around,
y, sorry.
it's the Y. Yeah. Since I'm revolving around the x-axis, I really care about that vertical displacement. So 2 times pi times y is my radius. But then what is my, is it to get the area, I have to multiply that length by some other length. So in this case, I'm going to multiply it by that little change in arc length. So that'll be ds. Or what we've done in Cartesian coordinates in the past is 2 times pi times y times 1 plus the square root, or no, plus dy dx squared dx. Ours is actually going to look really similar. In parametric form, we're going to integrate from A to B. 2 times pi times radius in this case is going to be y. So far, so good. It looks pretty much the same. But remember, the way we dealt with arc length in parametric is a little more specific. In the last example, it was dy dt and dx dt, but really my parameter is my parameter. I'm just giving it a different name this time. So basically, this is what I'm going to integrate. So again, to get these little like elementary surface areas, I need to multiply two lengths together. One length comes from the circumference of the circle. The other length comes from the length of the arc along that circle. And basically, I want to multiply all those things together, or add those things all together. I think it was Jacob who said a while ago, we only want to revolve the top, or I guess it could be any semicircle, but I really only want to revolve a semicircle because it's going to revolve all the way around the axis. So because of that, I'm going to integrate not from 0 to 2 pi, but from 0 to pi. I'm going to integrate 2 pi y, which we discussed that r sine theta is equal to y. And then dy d theta. I'm going to go ahead and skip a couple of steps here. But if anybody needs them clarified, just go ahead and stop me and I'll do a sidebar. Dy d theta is going to be r cosine theta. So squaring that gives me r squared cosine squared theta. Dx d theta is going to be negative r sine theta. But if I square that, I get positive r squared sine squared theta d theta. So this kind of thing just happened a little bit ago, where under the square root, that's all going to become r squared. So then I get 2 pi times r sine theta times the square root of r squared, which is just r, d theta. So then I get 2 pi r squared sine theta d theta. If I integrate that, I get 2 pi r squared times negative cosine theta from 0 to pi. Then I evaluate it there, I get 2 pi times r squared. Negative cosine of pi becomes negative 1, 1. And cosine 0 is 1. So this will indeed come out to be 4 pi r squared. So I know the integration to find a surface area is, definitely doesn't look any simpler than it used to, but hopefully it looks a little more familiar. Hopefully it makes sense why we've made the changes from Cartesian to parametric. If it doesn't, please ask me, stop me, ask me some questions. Any questions about how this example works, how this process works? All right. I'm going to go ahead and leave that one. If you want to get some additional practice with this, you can go grab these slides off of Canvas. But really, I would suggest kind of just, if you can kind of get behind the rationale of how this works, and really, the rationale is no different than what we did for Cartesian. You're still multiplying two lengths together, essentially the circumference of a circle and a small change in arc length. So that hasn't changed. It's just the only thing that has changed is how you represent that when you have a parameter involved. But if anyone wants to talk about this during our break or after class, we can go through it. Otherwise, I think it's a good exercise for you to practice with this. All right, I'm gonna go ahead and stop sharing while I open up the next thing. So now we're getting into polar coordinates. And like I said, I'll just remind you kind of, all these different coordinate systems. Why are we doing them? I am assuming that many of you are going on to Calc 3. And for those of you who are, one of the very first things you're going to be doing is basically getting away from one variable and using many. And that means migrating away from 2 dimensions into 3 dimensions. And there are more coordinate systems you're going to have to get used to, and basically certain coordinate systems make more sense than Cartesian, depending on the circumstances. So it really benefits you to kind of start learning. It's like understanding how to translate from one to the other and decide which one's better. So these are polar coordinates. So I'm assuming very few of you have seen this. So let's just go through the basics of what polar form really is. So before we do that, let's just kind of remind you of the way Cartesian coordinates work. I'm sure you're all comfortable with it, but basically this kind of helps you see the differences. So usually your independent variable is x, usually your dependent variable is y. You know that x gives you a measure of how far left and right you are with respect to the y-axis, the origin. Y gives you a measure of how far above or below you are, the x-axis. And I always express my points as ordered pairs, x before y. So polar, has a lot of the same pieces, they just don't mean the same thing. So in polar coordinates, my independent variable is theta. So, and the way you measure this angle is the way that you've been used to measuring it. Theta equals 0 starts with the positive x-axis. As theta increases, you rotate counterclockwise around the origin. So that's your independent variable. The dependent variable is r. Not a coincidence, r, basically it's a kind of analog of the radius. So r is basically how far away you are from the origin. Sometimes it's called the pole along that heading. And we'll get some examples of this that hopefully will solidify all these terms I'm throwing at you. But, instead of Cartesian, or sometimes you hear them called rectangular coordinates, where I'm just measuring, basically, where am I in this left-right direction? Where am I in this up-down direction? Now it's basically how far am I rotating around the origin, and then how far am I moving in that direction from the origin. And this is one of the things that I really don't like about polar. It's one of those things that, if I had discovered it, I definitely would have did this in the opposite order. But the dependent variable r is always listed first. So that's one thing to keep an eye on, because we're so simply used to looking at our independent variable showing up first on our points, but yeah, something to be wary of here. And just to kind of see how all these things are related. So, this point here, this solid red point, I can express that point in Cartesian form or in polar. And they'll both point me to the same location in space. You just have to be specific and be careful about what you're looking at. So yeah, you kind of know what x, y points look like. So let's focus on the theta and r. So theta basically gives you that angle with reference to the positive x-axis, and r is just a pure distance along that axis. So let's do some stuff with this. I just have a few ordered pairs here, and I'm going to plot the first one, kind of walk you through how it works, and then I will give you some time to think about the next 3, and I'll have you annotate my slides here. So first one, 1 comma 5 pi over 4. So just kind of going through this as slowly as I need to. The first thing I'm going to remind you of is that the dependent variable comes first. That's 5 pi over 4. So 5 pi over 4 is the 45-degree angle in quadrant 3 here. One thing that takes some care and some getting used to of polar coordinates is, you know, in Cartesian, the x-axis, we know how it's oriented. The y-axis, we know how it's oriented. In polar coordinates, basically I get a new axis with every new theta value. So maybe as you're getting started, it might be a good idea to trace that axis. So 5 pi over 4, if I graph that through the origin on the same heading, that'll coincide with pi over 4. But basically that'll make my axis like this. So basically whatever point I graph with that theta is going to have to wind up on this red line I just drew. The positive axis is going to be down here because that's the actual angle 5 pi over 4. The negative axis is going to be directly opposite that because that's in the exact opposite direction from 5 pi over 4. So I have my heading. I know that my point is going to be somewhere along this diagonal line that I drew. So where's it going to be? It's going to be 1 unit away, and I'll make this really explicit by calling it +1. It is going to be 1 unit away in the positive direction along this line. So that means my point winds up right here, 1 unit away. Any questions before I erase that? Because I want to give you enough room for you all to do the next few. All right, I'm going to go ahead and clear. So while I'm erasing, here's what I would like you all to do. Don't do it until I ask you to, but basically think about where that 0.2 comma 3 pi is going to go. I'll give everyone like a minute head start, and after that, I'm going to have you plot that point. So go ahead and work on that for the next few minutes, or sorry, next 60 seconds or so. And then when I give you the go ahead, start plot where you think that point needs to go. All right, go ahead and annotate and plot that point.
So are we all supposed to annotate?
Yeah, go ahead, and anybody who wants to, yeah. All right, I got a couple. They're in agreement with each other. So yeah, remember the independent variable is 3 pi. That's the angle. So let me start by asking this: is there maybe a more efficient logical way to express that theta?
Pi.
Yeah, pi is equivalent, right? So here's one thing I wanted to bring up between Cartesian and polar. If you have a point in Cartesian coordinates, it's unique. So if I say the point, 1, 3 in Cartesian, there is exactly one place where that so two ways to think about this. There's exactly one location that describes, and for that location, this is the only way to describe it. So that's a big difference between this and polar, because I have 2 comma 3 pi and 2 comma pi describe the same point. They describe the same location. All right, so let's go ahead and clear those off. I would like to get more than 2 or 3 for this next one. By the way, it doesn't matter if you're wrong. The penalty for being wrong is absolutely nothing right now. So this is the first time we're really looking at this. So next one, 2 comma negative 2 pi over 3. Whenever you're ready, go ahead and mark something down. Okay, so got a little bit of disagreement this time, which is a good thing to talk about. I don't want to annotate this. Okay, so just a reminder, so now we have a negative angle. So just a reminder, when you have a negative angle, so no matter what, you're counting, you're starting at theta equals 0. So positive is in the counterclockwise direction. Negative is in the counterclockwise direction. So basically, I want to sweep at an angle of 2 pi over 3 in the negative direction. And that's going to give me a terminal point basically here. So here is my theta axis. And the positive direction is going to be whatever that heading really is. The negative direction is going to be the exact opposite of that heading. So I have negative 2 pi over 3, which means that, what's my radius? 2. Yeah, I want to be on that second circle out. So I like this location here. So any questions on how this works? I think I may have some answers for the next one.
Can you explain how like the angle, the negative 2 pi over 3 again, like why it's right there? I don't get it.
Sure. So first thing I'll ask is this: are you okay with this angle here being, with the fact that this measures 2 pi over 3? Or is that part of what's confusing you?
I actually like, now that you drew the little angle thing, that makes sense
Okay.
compared with the other 2 pi over 3. Yeah.
Okay, good. So yeah, and just to kind of offer, oh, actually they're labeled, but if it was positive 2 pi over 3, it would be the exact same size angle. I would just be drawing it in the counterclockwise direction. So angle is negative 2 pi over 3. I think that's the part that's going to be the hardest for you all to get used to, just because you're so used to coordinate system where the axes don't move. Like that's just not something you've done. So I think that's going to be the hardest thing to get used to, which is why we're doing this. Any questions before I clear and move on to the next one? All right, last one, negative 3 pi over 4. This one might be a little tricky, so. But I still want to see you give it a shot. Yeah, while I'm clearing, think about where that point should go. So negative 3 comma 3 pi over 4. Whenever you're ready, go ahead and actually let me clear all the annotations before you do that, so I don't delete you. Okay, go for it. All right. Looks like I have a few. Can't tell exactly how many. See a few different colors in there. So again, we have angle of 3 pi over 4. So where is that? 3 pi over 4 tells us that just the positive sign tells us that our angle is going to be swept out like this. So that's theta equals 3 pi over 4. So I'll go ahead and draw in my so the heading 3 pi over 4 is this direction. So that is why that's the positive side of that, temporary axis. The negative side is going to be directly opposite it. So notice this, even though 3 pi over 4 puts me up here in quadrant 2, everybody who plotted a point plotted it in quadrant 4, which is correct, because if the negative axis is against that true heading, then our point should be over here. So to put one more point on a fine point on this. What if I wanted to restate this with a positive radius 3? What angle could I use to really get me the same point?
Seven pi over 4.
We'd use 7 pi over 4. Because if you look at where those points are plotted, that's exactly where they went, on that 7 pi over 4 heading. So yeah, be ready to, you can convert polar coordinates to other polar coordinates for this one. If I wanted to, I can call this one 2, 101 pi. There's no good reason to do that, but it's still correct. Because really, you can if you just add on a multiple of 2 pi, you're going to basically have gone around one full rotation and be back in the same place. So any questions on just how to plot these? Okay. All right, so now I want to convert a point from polar to Cartesian. So before I do that, why don't I have you all plot that point? And then we'll talk about how to convert it. So yeah, whenever you're ready, go ahead and annotate. All right, so I saw a lot of activity all in one place, which is a good sign. So how do I convert that point from polar to Cartesian? So let's draw a diagram here. So what I have, I mean, I don't really have the rectangular grids on here, but you can work with this. Basically what I want to find is my X and Y coordinates. And what you all have plotted for me is something in R, something in R theta form. So let's start with the R value, that value of 6. Where can I represent that on this triangle that I've drawn here?
The Y.
I do not believe the Y value, I don't think this Y value is 6.
Like the hypotenuse?
Yeah, the pure distance, the hypotenuse is 6. Y is something we're gonna have to find. How about the pi over 3? Where is that represented here?
It would be theta.
Yeah, so yeah, but I guess what I meant is, where is theta represented on this triangle?
It's to the left of the right angle.
Yeah, so that means always just like when you trace angles, the angle you're really tracing is the one included at the origin. So that angle is pi over 3. So how can I find, let's just start with X. How can I relate X to my polar coordinates? More specifically, what trig function relates X to my other measurements here?
Would it be sine?
Sine is the ratio of what, two sides?
It would be y over 6.
Yeah. So, okay, let's start with that. So I know that sine of pi over 3 is equal to y over 6 because of opposite over hypotenuse. Then what would I do to find y? And one note to make at the top here is, let's make this general. We got that y is equal to r times sine theta, which hopefully sounds familiar to something else we did earlier with, I think it was surface area. But yeah, y is equal to r sine theta. We can find this one exactly here. 6 times radical 3 over 2 equals 3 radical 3. All right, so how do we find x then? What trig function do we need to deal with in that for that one?
Would it be cosine pi over 3?
Yep, cosine pi over 3 is equal to x over 6, or x is equal to 6 cosine pi over 3. which is equal to 6 times a half, which is equal to 3. So my Cartesian coordinates are 3, comma 3 radical 3. And one more last note I'll put in here is x is equal to r cosine theta. So these are going to be really important ideas for, you know, one of the things we're going to have to learn how to do is to go back and forth between Cartesian and polar. And these are two really important ideas to go back and forth with. Any questions on how we did that conversion? Okay. Now let's go the opposite direction. I'll go ahead and plot this point myself. I know you don't need help there. So if I want 4, negative 4. So now I want to convert that point from Cartesian to polar. So again, oh, I don't want to do it like that. We'll save. So this time I have x equals 4. I have y equals negative 4. And now it is theta and r that are unknown. So how would I find either theta or r? Whichever one you want to start with.
Theta would be tan theta equals 4 sine over wait, never mind. I'm messing myself up. Isn't it negative 4 over 4?
Yeah, negative 4 over 4. How'd you know to do that?
Because tangent theta is opposite over equals opposite over adjacent.
So the tangent of the angle is, yeah, opposite over adjacent. So that's tangent theta. I really want to find what theta is itself. So I want to take the inverse tangent of negative 1, which is what? Hopefully a few of us were thinking it. So negative pi over 4, or negative 45 degrees if you want to work from there, which is totally fine. All right, how would I find r?
You can use the Pythagorean theorem, 4
Absolutely.
squared.
So r squared equals x squared plus y squared. And this is another crucial relationship to take note of. Basically, kind of saw how to get y in terms of r, how to get x in terms of r. This is another way to unite a lot of those quantities. So that is a general thing I would definitely pay attention to. R squared is equal to 4 squared plus negative 4 squared, which is equal to 16 plus 16 equal to 32, which gives me that r is equal to square root of 32, which comes out to 4 radical 2. So last question for you. What are the coordinates of this point in polar form? What comma what?
Four square root 2 comma negative pi over 4.
Yeah, definitely remember that the R value comes first. So we converted both directions. Any questions about how that's done? All right. So let's draw some curves now. So I am giving you the equation R equals 3. So R is a constant. If you think about what R represents in polar form, what do we think this graph looks like?
It's a circle, right?
Should be a circle, right? So basically, notice that, you know, in polar coordinates, I have two variables, R and theta, but for this equation, theta does not have any effect on R. So no matter what the angle is, I am 3 units away from the pole. And that is the exact definition of yeah, it's a circle with radius 3. So just to kind of make some connections here, if I were to represent this graph, a circle of radius 3 centered at the origin, if I were going to represent that in Cartesian form, what would that look like? What would that equation look like?
Like x squared plus y squared equals 9.
X squared plus y squared equals 9. So, and if you remember back just last slide, you know, we showed that through Pythagorean theorem, x squared plus y squared just equals r squared, right? So I get r squared equals 9, which is the same thing as r equals 3. So these things really do talk to each other, but obviously, you know, polar curves are all about, you know, representing things that are more rotational, if that makes sense. Hopefully it will with a couple more of these graphs, but yeah, the equation is much simpler in this case. Any more questions on why r equals 3 represents that circle? Okay. Now, how about one that doesn't involve r? What does theta equals 1 look like? In polar coordinates, what does theta represent?
The angle.
So theta is an angle, right? So let's go ahead and trace this angle out. Theta equals 1 is just a little bit bigger than 60 degrees. So there's that angle there. So I've drawn that angle. Does that give you any clue about what this graph actually looks like?
It would just be a straight line through the center.
Yeah, it's a straight line to the center on this heading, which I will try to do faithfully. So let me draw this out, and then I'll try to explain it in another way. So theta equals 1. Basically, you don't see r in there, so that means that it does not matter what r is equal to. So you can say that all these points have to, all these points satisfy this. So there's 1, 1, 3, 1, 5, 1, negative 1, 1, negative 10, 1. So really think about what's happening with, I just messed up, didn't I? No, I didn't, never mind. So all these different R values all have the same theta value to correspond to them, which means that basically if theta equals 1, then I just have to, basically what that looks like is on that heading, I can be any distance from the center, either on that heading or in the opposite heading. And that's how that graph is formed. So that's why it gives you that straight line that cuts through the center. Any questions there? Right.
Since-
Oh,
sorry.
go ahead, Mona Lisa.
Theta's an angle. It could be in like, sorry, it could be in like degrees too, right? Or is it only radian?
I have never seen a polar form dealing with degrees.
If we were
So
like, we're like on the test or on the homework, and like, because I think degrees are kind of like easier to like imagine than radians.
absolutely, yeah,
Can we like convert it, but then like just put it back? Okay.
yeah, yeah. There's nothing wrong with doing that. So I'll say a couple things about that. So yeah, I think probably everybody on this call is more comfortable with degrees than radians. I certainly am. And this is the first time we're looking at polar. So if it helps you, kind of helps you perceive and feel more comfortable, then yeah, you can definitely use degrees as a as kind of a middleman to get where you're trying to go. Hopefully you get to a point, and maybe that won't be this class, maybe those will be down the road. I don't know that I was comfortable enough to just go straight to radians in Calc 2 when I took it, but yeah, hopefully you get to a point where you can just deal with radians more directly. So I mean, I still am more comfortable with degrees than radians. But for example, when I'm dealing with polar, I just go straight to radians. And yeah, it's my hope that even though right now you kind of need those training wheels of degrees, hopefully you won't for very long. All right, so let's get a little more involved here. So I want to sketch this polar curve r equals 2 cosine theta. And then I want to come up with a Cartesian equation for that curve. So let's do the graph first. So I don't know what this looks like. So, you know, I imagine that what most of you did when you were first learning how to graph in Cartesian form was to come up with a few independent variable values and then find a few dependent variable values and then plot those on my graph. So I know that cosine theta has a period of what?
It would be 0 to 2 pi.
Yeah, so the period is 2 pi. So really you just, if you make an interval that's 2 pi in width, then you're okay. Let's just first one, I think it's kind of intuitive to just go with 0 to 2 pi. So let's go with these 5 points and see what we get. So I know when theta equals 0, r will be 2. When theta equals pi over 2, r will be 0. Cosine pi is -1, so it's be -2. 3 pi over 2 back to 0, and then this one back to 2. So I'm gonna go ahead and put this on you. I gave you 5 points here. Go ahead and start plotting those and see what you think. Plot those 5, and then if you feel comfortable, finish sketching the graph. So whenever you're ready, go for it. So are we just getting those 2 points over and over again?
Wait, shouldn't there be a?
Yeah, there should be more, right? So that tells us that we probably didn't graph enough points. So we chose the quadrant angles. They gave us really, so these 5 coordinates only gave us 2 different points. So let's go a little more granular. So midpoint of 0 and pi over 2 is pi over 4. Now let's just do 4 more points doing that. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So cosine of pi over 4 will be 1 over radical 2. So this will be radical 2. Cosine of 3 pi over 4 gives us negative radical 2. Negative radical 2, positive radical 2. So go ahead and plot those 4 and see if we get any clearer of a picture. So I got a couple more points in here. What do we think about this? Do we need more, or can we make some predictions about what kind of shape this is going to be?
Is it like a little circle?
Yeah, it's a circle. So I'll go ahead and trace that in. That was a horrible start. Let's try again. Not better, but I'm gonna stick it with it. Okay, so where do we think the circle center is? And let's go ahead, we need to find a Cartesian equation. Where do we think the center of the circle is? So give me XY coordinate for this center.
I'm assuming it's 0, 1
Be careful.
or 1,
1, 0, right?
0. Yeah.
What do we think the radius is?
1.
1. So that would definitely make sense with this graph. We know from our table that we've gone 2 units to the right. We know that this circle passes through the origin. So I would agree with that. So let's do this a couple ways. Can we make a Cartesian equation based on where we know the center is and where we know the radius is? So I'll remind you of this thing here. Basically, we can probably very long ago you dealt with this equation that lets you locate a circle in Cartesian form with any center. So in this case, our equation should be this: x minus 1 squared plus y squared equals 1. So I believe this is correct. Let's go ahead and confirm it using a second approach. So I know that r equals 2 cosine theta. I would really like to get this into a form where I can just convert this into Cartesian using those relationships that I know about. So I'm going to multiply both sides by r. So I get r squared equals 2r cosine theta. How can I re-express r squared?
X squared plus y squared.
Yep. How about r cosine theta? And I'll just draw a triangle over here to show why all this stuff is true. Here's x, here's y, here's r. If x and y are the legs of a right triangle, then r is the hypotenuse, then r squared equals x squared plus y squared. Falls out of Pythagorean theorem. And then trig also tells us that if x, y, r, and theta are all related to the way I've drawn them, then x is equal to r cosine theta. So this comes out to be 2x. And in the interest of time, I will just say this phrase: completing the square. I can complete the square on this equation here, and it'll give me x squared plus 2x plus 1 plus y squared equals 1. And then this side, basically these 3 terms come out to be x plus 1 squared. So I know I kind of waving my hands and asking you to take my word for it, but if you want to complete the square on that x squared plus y squared equals 2x, you will get that basically no matter how we got to this Cartesian equation, either from knowing what the graph looked like or by actually doing the conversion algebraically, you're going to get to the same place. So we okay with how we did this, how we got that circle, how we converted that equation? Anything at all about this one? All right, so I have 7:50. Let's go ahead and take a little break. We'll come back at 8 o'clock and we'll finish this one out. So I'll see you all then. All right, let's go ahead and get back to it. All right, so let's go ahead and sketch another one. I have two more. I'm just going to focus on this one. So I got r equals 1 plus sine theta. So let's go ahead and try the the quadrantal angles one more time and see if that gets us anywhere. All right. So 1 plus sine theta equals 1 plus 0. 1 plus 1 is 2. 1, 0, and 1. All right, so go ahead and start annotating, see if you see anything. I'll let you know this time that the graph is not a circle. But don't have a bunch of, I don't believe you're gonna get a bunch of repeats this time. So go ahead and start plotting and see what we come up with. All right, so right now, it looks like we start at the, at the right of the pole, go up 2 units above it, and then come back down to 1 unit left of the pole. But then it might not be clear what happens after that. Maybe you see, like, you kind of see this triangle forming, but probably not going to have straight lines like that. So let's take a couple more points. Specifically, it looks like it's from pi to 2 pi that's causing difficulties. So let's throw a couple more points in there. Let's go halfway between pi and 3 pi over 2. So that'll be 5 pi over 4. And then we'll also go halfway between 3 pi over 2 and 2 pi. That'll be 7 pi over 4. Sine of 5 pi over 4 is -1 over radical 2. So 1 minus 1 over radical 2. And then this should be the same value. So this is something like 0.293. So at 5 pi over 4, I should have something like that. Oh. Okay, so we got these 2 new points. So now let's try to follow it. So not a circle. We're gonna hit that pole and then kind of bounce off of it. It kind of looks like that. Any questions about how we got this? How would you describe what we just came up with? So the mathematical name, not that I'm not going to ask you this later, but just to point of fact, this is called a cardioid, which literally means heart-shaped. So yeah, this is a pretty standard curve you'll see in polar coordinates. Any questions about how we got this? All right, I am going to leave this last one. I'll post these slides. Well, I post these slides earlier. They weren't marked. I will post these later with my markings on them. Go ahead and clear some stuff off. But I will leave this one for you here for you to practice on. But this one, this shape is called a rose. And if you graph this out correctly, it'll probably make sense why it's called a rose. So if you want to practice this one, I think this is a good exercise to make sure that you can really kind of understand this process. Any questions there? All right. So don't really need to spend too much time on this. We're going to go into a little bit of differential calculus in polar form. But just to remind you of some things here we've already talked about. Remember that, the way we get R, really it's directly related to Pythagorean theorem. So yes, the pure distance away from the pole. The way R is related to X and Y comes from these trig relationships. So these definitely keep showing up. You're gonna so one of the things you're gonna be expected to do, and you'll see it in the homework if you haven't already, is converting between Cartesian and polar coordinates, things like that. And you're especially going to see it when it comes to calculus, which we're about to do now. So these two relationships here, I think these are things that are pretty straightforward to derive. So I'm not going to give you these equations for the final on Thursday. So yeah, just understand them, internalize them however you have to. But hopefully the way we went through it with the trig and the using Pythagorean theorem made sense. But if you need some more help, more clarity with that, just let me know. All right, so R equals 1 plus sine theta. That really is, we looked at it as the cardioid we just looked at. But now what we want to do is we want to find the slope of the tangent line. So what I want to do is, the slope of the tangent comes directly from dy dx. So, but the problem is there's no y, there's no x here. So I'm going to borrow a little bit of a technique from the parametric approach. So I'll start with dy d theta over dx d theta. Hopefully that looks familiar with the way we dealt with parametric curves. So now what we're going to do is find dy d theta and dx d theta. So still have the same problem. I don't have y or x in this equation. So how do we build that up? So here's one thing we know. We know that y is equal to, what's y equal to in terms of r and theta?
R sine theta.
R sine theta. So y is equal to r sine theta, which in our case is going to be equal to r, or sorry, we know r, 1 plus sine theta times sine theta, which is equal to sine theta plus sine squared theta. So now what we have is y in terms of theta. So now it should be more straightforward to do this, dy d theta. So I have y, which is a function of theta, so I should be able to take a derivative of y with respect to theta. So what is this derivative? Definitely would not hurt to polish up on our differentiation rules, because they can get a little complicated. What's the derivative of sine theta plus sine squared theta?
Cost cos theta one or cos theta one plus sine cos theta one plus sine.
Oh, you're
sorry.
going, yeah, you're going from product rule?
Yeah.
That's fine.
Sine
Okay.
theta.
All right,
And
keep going.
and the same thing again. Oh, sorry. That's it's not the same. Oh, it would be sine theta cos theta.
Yep, there you go. I'll do a rewrite here, because there's one thing I want to remind you of that we may have forgotten. So this comes out to be 2 sine theta cosine theta plus 1. No. Plus cosine theta. Does this look familiar to anybody?
It's cos theta.
It is actually sine 2 theta.
I apologize.
No, it's okay. So many identities. So, and the reason I bring this up is this is a kind of a common byproduct when you're taking derivatives like this. Let's do the other one. So the way we handled y. So any questions the way we handled y so far? Because it's going to be very analogous to the way we handled x. So we got x equals our cosine theta, which is equal to 1 plus sine theta cosine theta. And I kind of like the way we handled the first one using product rules. We'll do it again. So dx d theta equals negative sine theta times 1 plus sine theta plus cosine theta times cosine theta, which is cosine squared theta minus sine squared theta minus sine theta. All right, what is this right here? How can I rewrite that?
Would it be
One.
equal to 1 or negative 1?
No,
One
not quite.
minus 2 sine squared theta.
It's not equal to 1 minus sine squared theta.
Well, it should be 1 minus 2 sine squared theta minus sine theta.
Oh, this one on the right is not squared, it's just sine.
Yeah, it's gonna be one. The whole thing is gonna be 1 minus 2 sine squared theta minus sine theta.
Okay, that is correct. But there's a more simple way I can restate this. Cosine squared theta minus sine squared theta is actually cosine 2 theta. So I'll make a note up here.
Oh, cos A cos B sine A sine B, right? minus sine A sine B.
Can't really use that identity since all of our angles are just theta. I think you're thinking of the sum and difference identities, which are really good if you have, for example, something like this, sine of x plus y. Then you can use that one, but we don't really have. We don't have something of that form. So we have dy d theta, we have dx d theta. And by the way, I just want to point out before I go any further, this, me bringing in the double angle identities, that's more or less optional. I mean, it is optional, but it really makes what we're about to do next simpler. Because for me to get the slope of this tangent line, I need to do some substitutions, and I would really like to do as few of them as I need to. So dy d theta is equal to sine 2 theta plus cosine theta over cosine 2 theta minus sine theta. And I want to plug in pi over 3 for all those. So I get sine 2 pi over 3 plus cosine pi over 3 over cosine 2 pi over 3 minus sine pi over 3. So sine of 2 pi over 3 is radical 3 over 2. Cosine of pi over 3 is a half. Cosine of 2 pi over 3 is negative 1/2. Sine pi over 3 is radical 3 over 2. So minus radical 3 over 2. If I multiply numerator and denominator by 2, I get radical 3 plus 1 over negative 1 minus radical 3.
That's -1, right?
Oh, it's negative 1. That is really easy. So any questions on that? I'm going to have to make a copy of this slide and do the rest of it. But any questions before I go do that? Okay, go ahead and stop this for now.
I think you forgot the negative in front of the 1, like -1, right?
Yeah, I totally did. Thank you for that catch. All right. Oh, I can't read it. All right. So this next one, I may need some help remembering what I just had. So dy dx equals sine 2 theta plus cosine theta over cosine 2 theta minus sine theta.
Yes.
Okay, good. So I want the points where the tangent is either horizontal or vertical. So let's start with horizontal. If the tangent is horizontal, what does that mean about my derivative?
I'm sorry, the tangent is?
Yeah, if the slope of the tangent.
Okay.
So if the tangent is horizontal, what does it mean its slope is?
It's it's so big.
Not if it's horizontal,
0.
it's 0. I think you're thinking of vertical, Rios. So slope is 0 when I have a horizontal tangent. So that means I want dy dx to be 0. And in that case, it really, the only way that can happen given my dy dx is if the numerator is equal to 0. So from there, this equation would be pretty hard for me to solve if I leave that double angle identity in there. So I'm going to go ahead and undo it. So I have this equation 2 sine theta cosine theta plus cosine theta equals 0. I'm going to go ahead and factor out a cosine theta. So then I get 2 sine theta plus 1 equals 0. And that gives me these two smaller equations. We'll handle them one at a time. Cosine theta equals 0. What angles will that happen for? And for, let's just look at between 0 and 2 pi.
Pi over 2 and 3 pi over 2.
Pi over 2, 3 pi over 2. Good. And the other side, 2 sine theta plus 1 equals 0. That's going to give me sine theta equals -1/2, which gives me theta values of 7 pi over 6, I believe, and 11 pi over 6. All right, so before we go any further, let's look at the vertical. And in this case, that's where the slope is infinite. And the reason it's infinite is because if you have a vertical tangent line, that means you have a non-zero dy d theta and a 0, like basically no horizontal movement. So dx d theta is equal to 0. So you're dividing by 0, which gives, oh yeah, which gives you an infinitely, basically a slope approaching infinity. So in that case, I want dy dx to be undefined, which will give me cosine 2 theta minus sine theta equals 0. And again, I got a double angle I got to deal with again, or I got to undo. So hopefully, I mean, you probably don't remember these, but yeah, I mean, I will give you the double angle identities again on the test, but just know that cosine 2 theta equals 1 minus 2 sine squared theta. That's one of the 3 identities you can get there. I'm going to rewrite this as a quadratic where everything is positive, or the leading term is positive. 2 sine squared theta plus sine theta minus 1 equals 0. And how does that factor? Let me check that because I feel like I often do these backwards. 2 sine squared minus sine plus 2 sine. No, I think that's okay. So then I get sine theta equals 1/2. And sine theta equals -1. So this top one gives me pi over 6 and 5 pi over 6. And the only angle on the interval where sine is -1 is -3 pi over 2. I mean, 3 pi over 2. So look at all these different theta values I came up with. Are there any agreements between any of them?
3 pi over 2.
3 pi over 2. So let's, if we kind of remind ourselves what this this graph looks like, what happens at 3 pi over 2? So at 3 pi over 2, basically you have something undefined. You can see, and this is not really a formal way to look at it, but if you were to draw a tangent line at that, 3 pi over 2 is kind of where it comes back to the origin. If you were going to try to draw a tangent line there, it wouldn't be possible. Or basically there's a lot of different ways you could do it, because that is not, basically my derivative is not continuous at that point. So really the slope there is undefined. And I'll go ahead and remind you of one of our requirements we had for finding horizontal or vertical tangents. Let's just go horizontal, but really you can kind of reverse everything for vertical. If I have a horizontal tangent, that means my dy d theta is going to be 0. I have no vertical movement. So my rate of change in the vertical direction better be 0. But my rate of change in the horizontal direction needs to be anything but 0. Because I want to have horizontal movement in any direction. I just have to have some kind of change there. But I want to have 0 vertical change. So really, I need one of my derivatives to be 0, but I need the other one to not be 0. Because really, at 3 pi over 2, what you're going to have is the situation where dy d theta is 0 and dx d theta is 0, which is not well defined. Any more questions about this one? Okay. That's our last one. All right. So I got r equals 3 plus 8 sine theta. I want to find the equation of a tangent line when theta equals pi over 6. So I'll let you all drive this one. What should I do first? So what do I typically need to find let's start with the slope of a tangent line. What do I typically need to get the slope of a tangent line?
dy dx.
What was that, Rios?
Dy over dx.
dy dx. Okay. So I need to build dy dx, but I am in polar form. So what do I need to do to work up to that?
Just multiply r by sine theta for y and cos theta for x.
Yep. So y equals r sine theta, which in this case, that's going to be 3 plus 8 sine theta times sine theta. So let's go ahead and work with that. Last time we used product rule. This time let's do chain rule. So I'm going to expand this whole thing. And really, one's just as good as the other. Just I want you to. I'll show you a different look at this, just in case one makes more sense to you or one you feel more comfortable with. So 3 sine theta plus 8 sine squared theta. If I take that derivative with respect to theta, I get 3 cosine theta. And then since this one's a little more complicated, how do I take the derivative of 8 sine squared theta?
You can go ahead and do the same thing, like the product rule.
Let's try chain rule this time just to refresh it.
I don't know.
So the way I'm going to handle this is my outermost function is going to be x
Oh.
squared. What am I composing with x squared? I'm composing. Actually, I better make my outer function.
Cosine theta cos theta.
Yeah, that's what's going to happen, but I'm just kind of building up how that's going to work. So if my outer function is 8x squared, what function am I composing there is sine theta. So if I take the derivative of the outside function, that gives me 16x, but I want to keep sine theta intact. And then I need the derivative of sine theta, that's cosine theta. So that gives me 3 cosine theta plus 16 sine theta cosine theta. And like what usually happens, I got a double angle identity thing going on here. So I get 3 cosine theta plus 8 sine 2 theta. So there's dy d theta. Let's also do the same thing to get dx d theta. Okay, so dx d theta be equal to -3 sine theta. This one we're going to need. No, actually, I am going to get the double angle identity involved here before I take the derivative. So 3 cosine theta plus 4 sine 2 theta. So that derivative will be -3 sine theta plus 8 cosine 2 theta. Doing that gives me dy dx equals 8 sine 2 theta plus 3 cosine theta over 4 sine 2 theta. Nope. 8 cosine 2 theta minus 3 sine theta. So that's the derivative. Any questions about how we got this far into it? Okay, so now that we got the derivative, what do we do with it?
We would plug in pi over 6 for theta.
There you go. So theta equals pi over 6. So we got dy dx equals 8 sine pi over 3. We'll try to keep this all exact. Plus 3 cosine pi over 6 over 8 cosine pi over 3 minus 3 sine pi over 6. So sine of pi over 3 is radical 3 over 2. Cosine pi over 6 is a half. Cosine pi over 3 is a half. No, it's not. Yeah, it is. I did something wrong. Cosine pi over 6 is radical 3 over 2. Eight times a half minus 3 times a half. And it comes out to 11 radical 3 over 5. All right, so that is our derivative, which is definitely part of what we need for our, to get the equation of our tangent line. What else do we need to do?
What do we look at where it's horizontal and vertical slope?
We don't need that. We're just trying to find the equation of the tangent line at this one point.
Oh, that's just y equals mx plus c, right?
Yeah, so yeah, that's what our end goal is. Y equals mx plus b. Do we know anything right now about to get this this equation?
No, we have m.
Yeah, we just got m. And really all you need is m and b to get this whole equation. So how do I go about getting b?
Equate x equals 0.
Why x equals 0?
Because it's just y-intercept, right?
That's how you get the y-intercept, but so this slope we got, this slope we have, this 11 radical 3 over 5, that's only the slope at this one point, which might not be. It might not be on the x. It might not be on the x-axis.
Oh, yeah.
Is there some other way I can get x and y?
Convert to, oh, no.
So remember, we've kind of already done this. I know that x is equal to r cosine theta, right? So I can just plug in pi over 6 to my thetas. So then I get 3 plus 4 times cosine of pi over 6, which is radical 3 over 2. I get 7 radical 3 over 2. That's my x coordinate. I can do the same thing for y. I know that 3 plus 8 sine theta is again going to be 7 times the sine of pi over 6, which is a half. So that gives me 7 over 2 So now I have enough to solve for b, which is the last thing I need. So y equals mx plus b gives me 7/2 equals m, which was 11 radical 3 over 5, times x, which is 7 radical 3 over 2, plus b. So the good news is, like, I don't think all my radicals are going to cancel. So I get 7/2 equals 11 times 7 times 3. So 77 times 3, which is 231/10 plus b. So b is equal to 7/2 minus 231/10. Get a common denominator. We're almost there. So 35 minus 231. That's negative 196/10. Negative 98/5. So all these nasty numbers to get me to this equation. Y equals, where's my m? 11 radical 3 over 5, x minus 98/5. So kind of a long way to go, a lot of tricky algebra. Anybody have any questions there? All right. We only have about 25 minutes until 9:10. So that was the end of section 10.3. I'm going to go ahead and hold on to 10.4. 10.4 is a pretty short section. So we'll go ahead and do it at the start of class tomorrow, and then we'll spend the rest of the time reviewing. Otherwise, if there are no questions, I'll see you all tomorrow evening.
Wait, that's it? Like, we only have 10.4?
That's all that's left, yeah.
Was there a quiz due today at 5?
Due today? No.
It says that there was one due at 5 today. Quiz 14.
Oh yeah, sorry. That's the one I just uploaded. It's due tomorrow night. I'll change that.
Okay, cool.
Yep, that'll be due tomorrow at 5. All right, everybody, have a good evening.
All right, thank you, Professor.
Thank you.
I kind of have one more question, but it was like it's about my exam.
Okay.
For question 1, just like because when you were going over it today, I noticed that the last, so I think F and G, you put like an X on them, like they're wrong, but according to like the answers that you had posted for exam 2, like I
Mhm.
got the right answer, but you marked them wrong.
Okay.
But it would just be like 1 point extra or something. So I didn't know if I should tell you.
Oh yeah, of course you should. Yeah, let me go look at it, and yeah, I'll make whatever corrections to the graded book that I need to make.
Okay, it was just the first question.
All right, thank you for letting me know.
Thank you.
I was wondering if I could set up an appointment for you tomorrow.
If you could what?
Set up an appointment for tomorrow with you.
Yeah, what time are you thinking?
Whatever works best for you. I'm home all day.
Okay. Anything after 8 should be okay. I don't know what time you usually get started.
Could we do about 12?
Yeah, 12's good.
All right, thank you.
All right, no problem.
Professor?
Yep.
Yeah, it's me again.
Yeah.
Um,
What's up?
Professor, I was I was going through the entire like the polar coordinate stuff, like so you have those equations like on X and Y, and then you convert it to parametric, and then from that to polar. Is that what's happening?
I don't believe I ever explicitly went back to polar or to parametric.
No, it's just I don't know.
I mean, there was in taking these derivatives, I'm definitely treating theta like it's a parameter, but really the derivatives are handled pretty differently aside from that.
I mean, I'm a bit confused the way it's sort of like put down in a graph. Like I'm trying to reimagine it how it would look like how things are, or is it a completely different graph? Like um how do I put it? Like, you know, you have this you know, you showed the x and y like with respect to t, and then it has this weird sort of like graph, but then you're imagining that the t is sort of like a something, you know, it's outside the graph. It's not like in the graph. So is that the same principle that's being followed here? Like, you know, that
No, not for polar. I mean, in polar, you're graphing r versus theta, and both. I mean, there is a theta axis. It happens to rotate with every new value of theta, or I guess that you should call that the r axis.
Mhm.
Okay.
Yeah, but it's yeah, polar. Your both your variables, your theta and your r, are both absolutely visible.
That's really cool. Yeah, Professor, did you check about the Putnam exam, that the one that I sort of like asked you about?
Yeah, I couldn't. I mean, I looked it up a little bit, and I don't. I'm not sure what advice to give you other than can you get a hold of old tests?
I mean, yeah, I mean, I've been doing that, but it's just a lot of these stuff are like I mean, I know some of the material, but I just don't I don't know exactly like how to put it. Like I don't get hold I can't get hold of like what's gonna come, like what the syllabus is gonna be like, or I mean, I'm not gonna view it that way. It's just, you know, it's just a fun test, but
Yeah,
not like you know, I'm preparing for an exam, but still like it would be good if you knew, if you had a direction. I guess if that
I
makes
mean,
sense.
from what I could tell about that test and the way those things are usually designed is that, you know, the syllabus is really broad and expansive, so that you can't possibly prepare for all of it. Which is kind of annoying if you're trying to prepare for it, but yeah, I understand why they do it. I think the best thing to do is, you know, look at old tests just so you kind of get a sense of really what they look like, how they're structured, and, you know, look beyond what the answers are to the questions. Look more at